Hi, my name is Arnob, and my research dealt with the fundamental question of what a magnet really is, and the nature of the magnetic materials in general. Because generally when we think of a magnetic material, we think of iron, cobalt, nickel, completely metallic materials. But we really haven't considered the possibility of practical application of magnetism outside of the metallic regime, like with your plastics, your gels, your organic materials in general. So what I set about to do is I created the first ever general way to induce a magnetic effect in polymers. And polymers are the basis, for your organic materials, gels, your plastics, and they're these long polymers are long chains of carbon skeletons, and they have hydrogen atoms, oxygen atoms, nitrogen atoms generally coming off of them, but they're entirely metal free. And so I created that methodology for first inducing the magnetic effect in the polymers, and then I used a synthesis methodology, a simple aqueous-based synthesis methodology to create magnetic polymer nanoparticles, and which could have potential applications that we'll get to later. But that was basically the summary of what the fundamental question in science that I set about tackling. So this seems impossible, right? We don't really think that magnetic effect is really possible outside of metals because we're so used to seeing it only being restricted to the metals. But one of the classic examples, and we normally don't consider this that much, it's normally overseen, is liquid oxygen, because and it's normally overseen because you have to cool the oxygen you breathe in the air down to really low temperatures, right? But if you take liquid oxygen, let's say you cool it in a test tube, it's pale blue color, and if you take a magnet and you were to draw up the liquid oxygen, you could actually drop up a blue bead of liquid oxygen. And liquid oxygen is paramagnetic. It can respond in response to a magnetic field, and it's non-metallic. And so that kind of inspired me to thinking, wow, the magnetic effect is not solely restricted to metals. It's happening in other states of matter that we normally can't see, but it's happening nonetheless. And why does it happen? So I investigated that question, and it basically, when you have two oxygen atoms and creating the diatomic oxygen that we see in your liquids, in your liquid oxygen, they form what's called a molecular orbital. And in a molecular orbital, when we see the molecular orbitals for oxygen, we see two unpaired electrons. And unpaired electrons are the basis for paramagnetism, meaning that the material itself can be manipulated by a magnetic field. And so molecular orbital theory has a fundamental assumption to treat the atoms that feed into the molecular orbital as delocalized electron clouds. And that kind of inspired me to, when I was making my own synthesis methodology, which was I would take a water-soluble polymer like polyvinyl alcohol, I would treat it with some plasma and really knock off some free radicals along the backbone of that polymer, create those delocalized electron clouds, and then I used polycarbonate at the same time. I treated the polymer and polycarbonate at the same time to kind of create some stabilization, some of those stable lone spins. And then I would put an electron acceptor to make some charge around those lone spins and really complex the polymer because it's a long system. So molecular orbital theory really inspired me. The basis of my inspiration was that, and how to create magnetic polymer that could operate at room temperature and really had some appreciable strength to it. So why is this research so big? Why do we even really need it? So one of the applications that I was kind of looking at alongside when I was developing my research was an alternative form of cancer therapy called magnetic cancer hyperthermia. Has huge potential, huge promise. What's done is that they would take iron-based nanoparticles or nickel-based nanoparticles, and then since tumors actually have leaky blood vessels, that's one of the hallmarks of what makes a tumor differentiated from a normal cell. You could selectively size the nanoparticles, the iron-based ones in this case, that's what they would generally use, the metal-based nanoparticles, you could basically inject it into your body. It would go up to those leaky blood vessels. When you apply an external magnetic field, those particles that are trapped in the blood vessels actually create some localized heating, and this localized heating actually can destroy the cancer cell, tumor, and the tumors altogether with a very, very, very high efficiency, almost 80 to 90% cytotoxic efficiency, and very, very high rate of remission. Sometimes the rats that were used in these studies were cured of the cancer altogether. But the problem was, and this is the problem that kept bringing most of the rats actually out of remission, was the toxicity of the metals. So like if you have your iron or your nickel, they have bioaccumulation problems, they can't be really expelled from the body easily, they cause fibroblastic inflammation. So metals, I mean the metals are kind of limiting, we're kind of limiting the potential of magnetic hyperthermia cancer therapy. And so if the polymer though, if you were to use the magnetic polymer nanoparticles that I created, that can operate at room temperature and have that appreciable degree of paramagnetism, then you could put it in your body and you wouldn't have those toxic effects, and apply the magnetic field and still retain the high cancer cell killing efficiency. And if you look at the previous attempts of polymer magnetism that have been tried, they normally need to be cooled down to low temperatures, the polymer that's trying to be magnetized, to see any magnetic effects. And even the one room temperature study done in 2004 was able to create the magnet, but it took 3 months for the magnetic effect to even appear, so it wasn't instantaneous as my procedure is. And the magnetic strength wasn't even very appreciable, so you couldn't really use it for an application like magnetic hyperthermia cancer therapy. And the implications don't just lie in medicine, they could be in the environment. Your oil spill remediation is also one of the big factors of where metal nanoparticles are used. If you were to, metal nanoparticles can actually absorb the oil, and you can clean out your aquatic systems by just using a magnet to pull out the nanoparticles. But you have to dispose of the metals, right? And they eventually end up in our soil, our landfills, and really cause a lot of damage to our ecosystem. So water-soluble polymers that I was trying to magnetize would have really low environmental impact, and they already have a whole plethora of properties, polymers in general, and really coupling that magnetic component to them would diversify and absolutely explode the field of material science development in general. So that's pretty exciting if this research were to really get out there and further developed into being integrated into specific applications. So that kind of, this is, and from a societal point of view, this is not only limited to medicine, it can be also used in the environment, even computational data storage. And the scope of the project is big because now material science itself has kind of a new starting point, a new launching point to develop a whole class of materials, inherently magnetic polymers, organic materials. And this opens up the pathways and avenues for limitless possibilities in terms of how material science research can progress. Okay, so here what we see is actually the magnetic polymer at a macromolecular scale, even before nanoparticles are formed. You can see the magnetism. Okay, so to kind of contrast what we just saw with the polymer magnet, let's take a look at the iron magnet here, just your general black iron oxide powder. So what you can see by the comparison here is that the iron that we saw over in that other recording is actually comparable in the magnetic effect that we saw on the polymer, which is pretty huge in terms of describing the effect of what the polymer magnet here made really has. And here's a quick shot of the magnetic water-soluble polymer nanoparticles that I was able to create from that magnetic effect that you saw earlier in the polyvinyl alcohol that was magnetized.